Did you know that black holes aren't really black? They're very dark, sure, but they aren't black. They glow slightly, giving up light across the whole spectrum, including visible light. This radiation is called Hawking radiation, named after Stephen Hawking, who first proposed its existence. Hi, welcome to another episode of Physics is Easy with Mr. Jesse. This tutorial is on Chapter 26, Section 4, Consequences of Special Relativity, Time Dilation. In this lesson, we are going to investigate the concept of time dilation, use the formula of time dilation to calculate the time interval between two events, and resolve the twin paradox. Einstein's theory of relativity has two postulates. The first postulate is that all laws of physics are the same in all inertial frames. What do you mean by this? So for example, the Newton's laws of gravity, whether you're on Earth or you're on a spaceship traveling near the speed of light, is actually the same. The laws of acceleration, whether you are on Earth or somewhere else, would also be the same. That is what we mean by the first postulate, or the principle of relativity. The second postulate is that the speed of light in a vacuum has the same value in all inertial reference frames, regardless of the velocity of the observer or the velocity of the source emitting the light. What do you mean by this? So for example, we have here a light source, and so this is our light source, and we have here our observer 1. And on the other side is our observer 2. For example, this light source emits, of course, it emits light, and it is at the same time it is also traveling at the speed v. Now, according to this observer here, the second observer, the speed of light that he is going to observe would just be c. It's not going to be v plus c, but rather it would just be c. Also, this observer here would also see the speed of light. So remember that light is actually emitted in all directions. So the light that reaches this observer over here, even if the source is traveling in this direction, this observer 1 would still observe that the speed of light is c and not c minus v. That is what we mean by the constancy of the speed of light. Now, the constancy of the speed of light has been confirmed experimentally in many ways, so therefore the postulate of Einstein's theory of relativity, that light, regardless of the source or the observer, its velocity is not going to change. So relative motion is unimportant when measuring the speed of light. And because of the fact that the speed of light is constant, in relativistic mechanics, there is no such thing as an absolute time. And that leads us to today's lesson, which is time dilation. What do you mean by this? Like 1 minute for you may not necessarily be 1 minute for someone else who's traveling close to the speed of light. Also, there's no such thing as an absolute length. Like what's 1 meter for you may not necessarily be 1 meter for someone who is also traveling close to the speed of light. And to discuss the concept of time dilation, which is depicted in this equation over here, please pay attention to the next video.
Tick. Tick. So that's like the pendulum, the beam of light bouncing between the mirrors, and you could use that actually to build a very accurate clock. Then Einstein imagined what that clock would look like if it were moving relative to us. So what I'm going to have happen is Jim is going to be moved along the stage, keep moving the clock. And then we can dim the lights and we can see what that looks like from our perspective. We're stationary relative to Jim. And we've also got So there's a little box there you can see. That's Jim's head camera. So Jim is seeing, of course, the clock in exactly the way that we pictured it when it was stationary relative to us. The light beam is bouncing up and down between the mirrors. But if you look, and we've got a sort of little video effect on there so you can see the trail, you can see that the beam of light that we see is tracing out a triangular pattern across the stage. Beautiful. Thank you.
Can I get off now?
You can, yes. Thank you, Jim.
It was a bit fast.
Thank you. What a great use of that wonderful intellect. But it was beautifully demonstrated. What we saw there was, if I sketch it out again from our perspective now, from the audience's perspective, is that here are all those mirrors. So this is the light clock that Jim was carrying. But you saw that from your perspective, watching Jim move, the light took a kind of triangular path as it bounced across the stage between the mirrors. Here is what Einstein's postulate, if you like, Einstein's suggestion that the speed of light is constant for all observers, implies. See, this path is obviously longer than this path. So, if we all agree on the speed of light, then it is obvious that it must take the light longer to tick for the moving clock than it does for the stationary clock. Moving clocks run slowly. This is true. Time really did pass at a different rate for Jim. It passed at a different rate for him than it did for you in the audience watching Jim move. There's no sleight of hand here. Jim really is a time traveller. Our time is personal to us. This is what Einstein had discovered. There's no such thing as absolute time. Now, why don't we notice this in everyday life is because the amount by which time slowed down for Jim was minuscule because the speed he was travelling was so small compared to the speed of light. But if we'd have sent Jim off in a rocket, would you like that? A rocket, just flying out into space. Let's say that we catapulted Jim off at 99.94% the speed of light for 5 years, according to his watch. Then we tell Jim to turn around and come back. It takes another 5 years to get back to the Earth. So for him, the journey would take 10 years. But for us, with our watches ticking faster than Jim's, 29 years would have passed. Jim would return in 2042, having aged only 10 years. It's a real effect. He'd be a time traveller. Time travel into the future is possible.
And here is the equation for time dilation. We have delta t, or the time interval measured in the system in relative motion with respect to the clock, is equal to the proper time delta tp, or the time measured in the system moving with the clock, divided by the square root of 1 minus v squared over c squared, where v is the relative speed of the system with the clock and c is the speed of light. Now take note that delta t rather is greater than the proper time, and also motion is relative. So for example, if you are on a bus and I am on the road looking at you riding on the bus, I would say that you are the one moving past by me, but relative to you looking at me and you're on the bus, then you could actually say that you're at rest on the bus and then I am the one moving past by you. That is what we mean by motion is relative. So motion actually depends on who's looking and whose perspective. Here is one of the problems that would allow us to apply the concept of time dilation. Now, in solving problems related to time dilation, the biggest challenge among students is to identify whether the time given is the proper time or the dilated time. Now remember, The dilated time is the time observed by somebody who is moving relative to the clock. So therefore, the time that is measured by someone who is at rest with the clock is the proper time. Let me say that again. The dilated time is the time that is measured by an observer moving with respect to the clock, whereas the proper time is the time measured by the observer that is at rest with the clock. So having that, let us look into this problem. The period of a pendulum is measured 3 seconds in the inertial frame of reference of the pendulum at the Earth's surface. What is the period as measured by an observer moving at the speed of 0.950 c with respect to the pendulum? So the question itself would tell us that we need to solve for delta t. So the time that will be measured by an observer that is moving with respect to the clock. And therefore, this 3 seconds here is actually our proper time, or the time that is measured by someone that is at rest with respect to the clock. So to solve for delta t, we just have to use the equation delta t is equal to the proper time interval divided by 1 minus v squared over c squared. So the proper time is 3 seconds divided by 1 minus the velocity of the other observer that is moving. So that is 0.950 c. And don't forget to square the entire value divided by c squared. So manipulating this equation, we will have 3.00 seconds divided by the square root of 1 minus 0.950 squared, since the c is gonna be cancelled, and that would approximately give us our dilated time is 9.61 seconds. So hence the moving observer considers the pendulum to be moving, and moving clocks are observed to run more slowly. So according to the person that is moving at the speed of 0.950, the pendulum or the clock is observed to run more slowly, while the pendulum oscillates in 3 seconds for an observer in the rest frame of the clock, or the observer on Earth with the clock. It takes nearly 10 seconds to oscillate once according to the moving observer. To summarize time dilation, the time interval delta t between two events measured by an observer moving with respect to a clock is longer than the time interval delta tp between the same two events measured by an observer at rest with respect to the clock. Therefore, delta t, once again, is much greater compared to the proper time. Also, a moving clock past an observer at speed v runs more slowly than an identical clock at rest with respect to the observer by a factor of 1 divided by the square root of 1 minus v squared over c squared. This effect is known as time dilation. Now, time dilation is a very real phenomena that has been verified by various experiments. Now, here's the interesting part. When time is dilated, all processes, that means chemical, biological, as well as physical processes, are slowed down. This means then that if you have a twin and you go out to space travel and you travel near the speed of light, maybe 5 years away, and then you go back to Earth and for another 5 years, by the time that you come back to Earth, your twin could actually be much older than you are. You only age 10 years because for you, you traveled 5 years towards your destination, then back for another 5 years, so you age 10 years. But for your twin who is actually left on Earth, he could age more than you do. So this is called the twin paradox. And to resolve this twin paradox, please view the next video.
The special theory of relativity was introduced by Albert Einstein in 1905, and this theory deals with inertial reference frames that are not accelerating. Now, this theory predicts that the time will slow down for objects that are traveling with very high speeds relative to their stationary counterpart, whose reference frame is an inertial reference frame. So the theory of relativity, Einstein's special theory of relativity, basically predicts the concept we know as time dilation. Now, shortly after Einstein's publication of the special theory of relativity, an apparent contradiction to this theory was pointed out, and this contradiction became known as the twin paradox. Now, the argument to this theory goes something like this. So the argument deals with a pair of identical twins who are of a certain age, let's suppose 25 years of age. Now, one of these twins climbs into a spaceship that travels to a very distant star with a very high velocity. It travels there and back, while the second twin remains on Earth. Now, if we take the reference frame of the person, the twin on Earth, and we apply the special theory of relativity, we will get time dilation. So basically, the person inside the spaceship, the twin inside the spaceship, will age less than the person on Earth. So once again, if we take the reference frame of the twin on Earth and apply the special theory of relativity as discussed above, the twin on the ship will return younger than the twin on Earth. That is, the twin on Earth will age more than the twin in the ship. And this is known as time dilation. And the equation that gives us by how much older the person on the Earth will be is given by this formula. This is the time dilation equation. So once again, we have the person on Earth, which is assumed to be stationary, and that's person number 2, twin number 2. Now, twin number 1 climbs onto our spaceship, which travels with a very high velocity there and back. So basically, when the trip actually takes place and the spaceship returns to Earth, the person, the twin on Earth, will be older than the twin inside that spaceship, and this is known as time dilation. Now, what happens if we take this argument and reverse the argument? What if instead we choose the reference frame of the twin inside that spaceship? Now, in such a case, the spaceship is now assumed to be stationary while the Earth is the object that moves away and then back again. Now, if we apply the special theory of relativity to such a situation, we see that the stationary twin in the spaceship will now age more than the twin on the moving Earth, because now the Earth is moving away and then back, so the Earth is moving with the velocity, and that means by time dilation, by the concept of time dilation and the special theory of relativity, this person who is assumed to be stationary inside the spaceship will age more than the person, the twin, on Earth. Now, this is the exact opposite of what we obtained in this earlier argument. Is this a contradiction to the special theory of relativity? And the answer is no, it's not. And the reason for that is by what we said earlier. So we said that the special theory of relativity deals with inertial reference frames. So recall that the special theory of relativity can only be applied to inertial reference frames, which are reference frames that are not accelerating. Now, the spaceship accelerates when it begins a trip. It accelerates when it turns around, and it decelerates when it returns back to the Earth. So that implies that the spaceship is not an inertial reference frame. It's a non-inertial reference frame because the spaceship accelerates. Now, the Earth, on the other hand, can be considered as an inertial reference frame. Therefore, since twin number 2 is always on an inertial reference frame, the special theory of relativity can only be applied to the twin that is found on the Earth. So that basically means our reference frame is the Earth, and that means the person, the twin on the Earth, will be the one to age more compared to the twin in the spaceship that will age less.
And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.